We want the bullet to hit a target 10 meters away. Now hit the slug with the hammer and see what happens. The bullet will fly out in a straight line. We'll try it again with more force. This time the bullet will probably spin out and tumble and hit the target. Then we put the slug in the barrel. We hit it with the hammer. The slug will fly in a straight line down the barrel and spin around and hit the target. But this is a theoretical experiment. In reality, we can't propel the slug with a hammer. So we'll try it with a small explosive. The explosive creates a high-pressure gas inside the barrel. The slug flies out of the barrel quickly and hits the target. But that's still too much trouble. We'd have to release the slug and fill it with explosives every time. It's a cumbersome and inefficient process. So we improved the design. We added a shell casing to fill the shells with explosives and designed the primer to detonate it from an external impact. That made firing and loading more efficient. But the hammer wasn't enough. We needed a trigger to replace the hammer. We designed a hammer at the rear of the firing pin. The hammer is attached to a spring at the bottom of the stock, so that when the hammer is triggered, the spring is compressed and the hammer is released to complete an impact. We then integrated the firing pin into the barrel bushing. When the barrel bushing is pulled, the firing pin section pushes the hammer back to build up force. The front part of the barrel bushing is fixed. The nearby spring is connected to the base plate. Automatic reset after pulling the bolt. After the hammer has built up its power, it needs to have a fixed potential energy, ready to be activated. Next, we need a set of mechanical connections to accomplish this. We use a component to hold the potential energy of the hammer. The hammer is held in the ideal position by a specially shaped design. And then we connect it to the trigger, so that when we pull the trigger, we can release the hammer. But the part that holds the hammer in place doesn't automatically reset itself. We'll need to add a spring plate to make sure it resets. At this point, the main design of the pistol is complete. The next step is to consider the bowing of the pistol. We designed the magazine to be removed by sliding the bullet out. The first shot requires a single pull of the holster, which simultaneously builds up the hammer and pushes the bullet into the barrel. In order to smooth the bullet into the barrel, we designed the barrel connected to the bottom handle with a small tilt. Each time we pull the holster, the barrel will be slightly tilted downward. The bullet will enter the barrel more smoothly. At this point, you pull the trigger to release the hammer. It hits the firing pin to complete the shot. The ammunition explodes and burns, pushing the bullet to release kinetic energy. At the same time, the recoil of the exploding bullet will push the holster to slide backwards, automatically ejecting the shell and pushing the bullet into the barrel. And that's the perfect pistol. Wait a minute, we're missing a key point here. The bullet explosion is instantaneous, so fast that when the recoil pushes the holster to its limit, our finger is still on the trigger and we can't release it. At that point, the part hasn't even been seated. The hammer automatically strikes the firing pin as the barrel resets. This is the same as pulling the trigger once and firing a round. In order to prevent this from happening, an isolation part has to be designed. The isolation part can only drive the hammer when the trigger is pulled, without affecting the reset of the hammer, so that the top hammer will automatically hold the hammer each time and release the hammer with the next trigger pull. This is the perfect design for an automatic pistol. You got it?